Hello, hello. I think I'm live. Okay, today we are going to read the attention following need paper. So I have actually read this paper once. So this is probably going to be very fast. Uh, yeah, that's a plan. Yeah, but it's been quite some time since I read this. So I'd like to read this again. That's the plan. Okay. Attention following need by Ashish Vishwani. We have, yeah, it's by Google. So this is a paper that introduced transformers to the scene, and as we all know, transformers is arguably the greatest invention in the field of artificial intelligence ever. Okay, so a dominant sequence transaction models are based on complex recurrent or convolutional neural network that include encoder and decoder. The best performing models also connect the encoder and decoder to attention mechanism. We propose a simple network architecture, the transformers, based on solely attention mechanism, dispensing with recurrence or convolution. So entirely. Experiment on two machine translation tasks show that the model to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 in blue and on some okay. Hmm. Okay. After training for 3.5 days on 8 GB. Okay, we show the generics will not the task. Okay, cool. Introduction. RNN have shorter memory and gated recurrent neural networks in particular. I mean, RNN, LSTM, okay, have firmly established themselves, sure. RNNs are typically, okay. And the persons for stepping computer 7 they generate a sequence of hidden state. The incoming sequential nature pollutes parallelization with training examples becomes critical longer sequences, sure. They are not at all parallelizable. Agent mechanisms have become an integral part of compelling sequence modeling and transaction models in various tasks, allowing models of dependencies without allowing modeling of dependency without regard to the distance in input or output sequence. In the work, we propose transformers. Background. The goal of reducing sequential computation also for foundation of extended neural GPU. In these models, just 1 second. Self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute representation for the sequence. Self-attention has been used successfully in variety of tasks, including okay. End-to-end memory network. To the best of knowledge, I will transfer the first transaction model to relying entirely on self-attention. Okay. Model architecture. All right, let's read the architecture of a model. All right. So model architecture. Most competitive neural sequence transaction. What does transaction mean? Transaction in AI. Reasoning from observed. Okay. A model that's capable. Okay. I mean, what is it called? Markov models, right? Markov assumption, right? Condition independent given problem in LLMs Pressing the next word, the model only needs to consider only current word and the word behind it. Yeah, that would be true. What is this? Obsidian Tools panel. Oh, I know that. Okay. Now I don't want you. Okay, thank you. More architecture. It has an encoder decoder structure. Here, the encoder maps an input sequence to a sequence of continuous representation. Okay, this is the transformers. The transformer follow this overall structure using stacked self-attention and pointwise fully connected layers for both the encoder and decoder, shown in left and right halves respectively. We have the input, which adds position encoding and goes through a sequence of encoder. The sequence of encoder blocks, which creates what is it called? Uh, Context. This will go through a series of decoder blocks. And that's how transform works, right? Encoder. Encoder is composed of a stack of 6 identical layers. Each has 2 sublayers. First is multi-edge self-attention mechanism. First is a multi-edge. Second is a simple position-wise fully connected network. That is, they are parallel. They are position-wise. The input of each sublayer is okay. This is the normalization, and this is the what is it called? A residual connection. Decoder. The decoder is also composed of a stack of n equal to 6 layers. Okay. Attention. Scale output attention and multi-head attention. And this is the attention. In practice, we compute attention function on a set of queries simultaneously packed together into matrix Q. So the matrix Q contains queries. Okay. The two most commonly used attention functions are additive attention and dot product attention. Dot product attention is identical to algorithm. Additively compute the compactability function using feed-forward network. The singular. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it's optimized using highly optimized matrix multiplication code. Other file for some values of decay. Two mechanisms perform similarly. Additive outperforms dot product without scaling for larger values of decay. We scale the dot product. Oh, okay. Okay, why scale? multi-head attention. Instead of performing single attention function for QKV, we found it beneficial to linearly project the query key value such times with different learned linear projection respectively. On each of these projected versions of QKV, we then perform attention function in parallel. These are concatenated once again projected, resulting in the final values are depicted in figure 2. Okay. We call particular attention. Okay. These are concatenated and once again projected, resulting in final value. I think it's better now if I look at anti-capitalist code. Maybe a nano GPT, I just need normal transform. This is probably it. Okay, we get the data set, we print it, we take the vocabulary, we create a we create encoding. Okay, we do that. We create the data set. Okay, bigram rank is model now. Probably just makes it within a grad, but it shows a temporarily disabled gradient computation. When this, okay, how is it different from using with the torch dot now that. Okay, basically same, but okay, cool. Estimate loss. Hmm. I don't ever use this thing ever. I should start using it. Okay, class head. Okay, this is one head. Then we do that to create multiple heads. This is fade forward. We probably use both of these to create a block. It's a diagram also. Probably it's a transform. Okay, diagram. Okay, cool. Okay, we have key, which is a linear embedding error. We randomly generate key query and value QKV. Then okay, this is actually the whole. This matrix contains all of the key for each of the token, more like token index. So we extract the correct key. Compute the attention score and do it and run the prediction. This looks simple actually. For multi-head attention, we have had this NN.modulus. I have no idea what that is. NN.modulus. Okay, or submodules in a list. My module. So linear is equal to another modules of for I comma ln enumerate several linears. So linears of I. Where can I hide or indexes of things? Okay, cool. Oh yeah, I didn't know this. Little bit of one thing I don't understand is the use of NN modulus and can I when I should use one and the other? Not really. Maybe there's some situation where you can but the main idea is the in NN sequential, the NN modules stored inside are connected in the cascaded way. For give me a second, I'll be back. 1 second. Yeah, sorry about that. So where were we? Yeah, come on. Oh, take me there, man. In another sequential, the modules are connected and cascaded by, for instance, the example that I gave. A neural network that receives as an input an image. I mean, I want an example actually, so I know somebody who can give me a good example. Essentially designed to store a collection of TORS modules. It doesn't impose any specific structure or order. When you need more control over the layers or forward path, you can dynamically decide how to, okay. We can do like element module list of this thing. The for layers and layer, okay. Okay. In an define sequence of layers that execute in the order that is defined. It assumes a straightforward linear computation graph and automates the forward pass for you. Okay, so I probably don't have to do this. Okay. Hybrid use case. You can combine both when needed. Shared layer equal sequential module. For learn dynamic layers, okay. Show me code for MNIST using bot. Oh no, I mean not bot. I mean use both of them individually. Ma, ma, ma. Okay, fine. Give me code for MNIST model using basic CNN using nn.sequential. We'll ask them individually. So we do all this. Self-dot model equals nn.sequential of. Okay, we do this. And in the forward function, we just do self-dot model of x. It just goes to everything. Okay. Now do the same with nn.module list. Okay. So in the sequential, we have this. So how do I train the model? No difference, right? Where's the model? Model.train. Optimizer output equal model of data. We calculate loss backward optimizer. Where is 0 grad? Yeah, there you are. Cool. Okay, now I'm using module list. Conv. Define pool, module list of pool. Okay. First convolution layer equals value of convolution. Okay. It is just a collection. It is just a list of not even a list. Yeah, it is a list. The list. Okay, module list. Yeah, sure. Nothing difficult here. We learned all that. Now go. Cool. Heads equal to n.module list of head. Okay. So each of them will do what is called self-attention. Then we projection dropout. out equal to concatenate, do all this and then concatenate the output, and then we project and give out. So what is the output of multi-head attention? Probabilities, right? Transformers AI. So multi-head attention the output is probably some linear combination. I mean, I don't know. What is the output of the multi-head attention layer from a transformer? Honestly, I would like to ask ChatGPT this question. Combination of attention weighted values across all attention heads. Okay. So what I get is attention score, which will be multiplied by the value. So I think what I get is probability distribution across the whole vocabulary, or maybe something in between. Maybe I get that after passing through the linear lines. I'm not sure. Then we have linear, less simple linear followed by non-linearity. We have a ReLU, we have a dropout. Dropout happens after. That is very weird. Give me some second. Block. So this block, we have multi-head attention. Then we run it through a feed-forward layer. Forward equal to the one block. Yeah, x equal to x plus this thing, and then we do this. This is because of what is it called? Then where the layer num? Okay, we do layer num here itself before passing through the fully. Before multi-head attention video. So this is pre-layer now, right? Which is not what is shown here. Cool. We do the layer normalization before passing the model into the like multi-head attention and feed forward again. And we add this because of residual connection. This looks easy, man. I should be able to do this. With the help of this thing, 100%. Okay, I think I'll do this tomorrow. Okay, now we have bigram language model, the whole model. This is one block, right? We have embedding, positional embedding, block, okay. Blocks, which is another sequential Oh, we do the sequential here. A module is there. That's cool. The thing we learned. Block for number of head, number of embedding, for number of layers. So, what block is this? Oh, yeah, this is a GPT, right? That's the encoder. That's not the decoder. Okay, okay, okay. Cool, cool. Cool, cool. Bigram language model. So in the forward, we do self.talk and embedding of the index. Then we do partial embedding of dots.arrange. Okay, in some way we add the partial embedding. Not the way which I think I would use, but a way nonetheless. Then x equal to talk and embedding. Oh, this is only the partial embedding. Then we add them. Okay, okay, that makes very much sense. Then we pass it through a sequential of, let's say, I don't know how many blocks, 12 blocks. Then we do layer normalization. Why do we do that? Probably that's a layer normalization required somewhere here. GPT-2 architecture. Also, this is pre-layer norm. That's kind of cool, right? That's cool. If targets is none, loss equals none. Otherwise, we go, okay, this is probably for inference and training difference. Then when you say to generate, I index is bt, crop index, get the prediction, apply softmax, focus on the last time step. Okay, we only take one. Then we apply softmax of the probabilities, then sample from the distribution. We use star multinomial. Multinomial. Can someone please know? With numpy more or less clear. It takes a number of turns with probabilities for each income. Return drawn indices where numpy returns count of the drawn indices sample. Okay. Returns answer where each row sample from which okay. A stricter definition would be multivariate. The rows of input doesn't need to sum to 1. In which case, we will use the value as weights. But must be non-negative, finite, and have a non-zero sum. Yeah, but this one is greater than 0. Cool. Okay, then we concatenate, append the sample index to the running sequence. For each max new targets. And we return index. Hope this is some like appending. Model equal to bigram language model. M equal model to device. In the number of parameters. Optimizer equal to LW learning rate. Okay, that makes sense. I think I learned it. So where does the query key, all those things come from? We randomly initialize it. And then during training, each row gets updated, or column, I'm not sure. They get updated. We plug the correct index. We plug the correct row from the query key value matrix, and that query is probably updated by gradient descent. I mean, by gradient descent. I'm using gradient descent loosely. Head I just have to make the forward function. Or the PyTorch will take care of the rest for me. Position-wise feed-forward network. In addition, each of the layer in our encoder decoder is fully connected, which is applied to each position separately and identically. Okay, this is done for parallel. I want to see that fully no feed. Yeah. Oh, you don't do anything. Okay. The dimension of input and output is this. The inner layer has the dimension of this. Embedding is softness. Use learned embedding to convert input settings and output into vectors. We also use the usual learned linear transformation and softmax function. Yeah, one is the total computational complexity per layer, and is the amount of computation that can be parallelized. Third is the path length between long and depends on. In this section, we compare various aspects of self-referential lecture recurrent. Okay. Parallelization is one other thing. Computational complexity. Third is the path length between long range dependency. Okay, okay, it's the key. Okay, cool. As noted, self-referential connects all positions with constant numbers or sequential execute operation, whereas recurrent require on sequence. Okay, I'm going to ignore that. Training data, we trained on English German data set. 4.5 million training layers. Okay. NVIDIA P100. NVIDIA. Wait, what? What happened? Oh, I didn't know. Okay, I meant NVIDIA P100. Like VRAM 60 GB. Oh, versus let's say yeah, pardon me, sorry. It's pretty cheap. That's a lot of RAM though. Hardware and scheduler. Sensor encoded using byte pair encoding. Okay, which has shared source target of about 37,000 for your investment. What is the vocabulary size? Okay, vocabulary size is this 37,000. Okay, for English fund we use significant larger WMT. What is WMT in AI? Machine translation. Okay. WMT, it's a data set. It's the name of a data set, I guess. Split into a 32K word piece vocabulary and split them back together. Each training batch contains a set of sentences. Compare this many and this many target tokens. We trained the modern 8 NVIDIA P100 model parameters. Each training step took about 0.4 seconds. We trained the base model for 100K steps for 12 hours. For a big model, let's suppose 1 second. Optimizer. We use Adam Optimizer. This looks default with learning rate. Cool. I think I can replicate this thing. I genuinely can. The only thing is they use a full transformer model. Well, I use a decode only model. All right. Regularization. We employ 3 regularization, residual dropout. Basically, dropout is 0.1. That's small. Label smoothing, you telling me about label smoothing. Yes, hurts perplexity. As a model learns to remove unsure but improves accuracy and juice cut. Results. Okay. When this work, heavy percent transformers. Okay, for trans. Okay. The code to train the evaluate is available. Oh, TensorFlow slash tensor to tensor. TensorFlow slash tensor to tensor. Public archive. Uh-huh. I guess. All right. So that's it. I think I'm going to end the stream there. Maybe not. Okay, this is a visualization. That's cool. Cool. And I think I will be it for the stream. So thank you for watching and